Question 87 is which of the following is closest to the diameter of the radio bubble? First of all, I want you to think about something. Uh, so the the minimum you probably know is the relationship between the radius and the diameter. And so yeah, you know that a diameter is twice the size of the radius. So if you have if you have a source here and the sound is leaving the source, okay, so it's leaving the source and we're watching it travel away, so it makes this bubble, then this is going to be the radius. And you can imagine it like a circle, and this is the radius, and so the diameter is going to be twice the radius. Now, why would I bring up such an elementary thing? Is because look at the answer choices. You see that there are, among the four answer choices, two of the choices are exactly double two of the other choices. And this is helpful to notice because it helps you to catch a very simple mistake that you might make, which is you calculate the radius, but you forget to double it. So in order to get the diameter. And it also shows you that even if you had no clue what was going on, you have a 50-50 chance just by noticing they're asking for the diameter. So what are the chances that two answers are exactly double two other answers? It's extremely unlikely unless it's a trap that some people are putting radii instead of the diameters. Okay, so I'm just putting that in the back of your mind for when you're caught in a situation. But this is going to be a matter of dimensional analysis. So we're given 1 light year is this distance. And well, we can translate this into a mathematical way of saying it. Instead of saying 1 light year is this, because we know this is the distance traveled by light in a year. Another way of saying in a year is per year, right? Isn't that a common expression that we would say this is what happens per year? And that is translated directly in math as a ratio or a fraction. So I can rewrite this as 10 to the 16 meters per year. So that's a translation of this information provided in the passage. And so all I need to do using dimensional analysis, because I know all my answers are in meters, I can see that in the answer choices. So I want to get rid of the years. So the only way to do that would be to multiply this by the number of years. I'm giving 100 years, which is the same thing as 10 to the power of 2 years. So dimensional analysis is paying very close attention to the units in order to get what I want. Sometimes you're going to have to divide. Sometimes you'll be multiplying. It depends on the problem. It depends on the units that you start with. So just paying attention to the units can solve many problems on the real exam. In fact, here's an expression that I often use in the tutorials is that dimensional analysis is such a powerful tool. It can allow you to get questions right, even when you don't fully understand the question. So you might not understand exactly what they're asking, but because they provide the units in the answers, and they provide obviously units in the passage or in the question stem itself, because of that, you can manipulate the units in order to get to the objective, the units in the answers. So years cancel, and I'm left with meters. That concludes dimensional analysis. It's over because we have we've analyzed the dimensions to get what we want. The rest is just mathematics. So what do we have? Same base, you add the exponents. We have 10 to the 18. Now, remember what we just calculated. A sound started somewhere, and then it expanded. It went off into outer space in this bubble. But the sound started somewhere, and you know, these microwaves, it's not a microwave, it's a radio transmission. These are electromagnetic waves. So because this is part of the electromagnetic spectrum, like ultraviolet light, like visible light, all part of the electromagnetic spectrum, they move at the speed of light. And so it's moving at the speed of light from this point. So we're actually just calculated the radius. And then if we want the diameter, so this is going to be the radius. So then the diameter is twice that. Is there any questions about that before we look at the question 88? Okay, so question 88. So extraterrestrial life. Nice to have that on a real exam, because the signals lose intensity at a rate inversely proportional to what? So we want to know the rate at which the intensity of this electromagnetic radiation will be lost. And do you remember? Do you remember that I underlined when we were looking at the Master Series questions 8 to 10 about the fact that intensity is in units of watts per meter squared? Watts per meter squared. Well, watts is power, and obviously meter squared is area. So watts per meter squared. And yes, indeed, the answer is C. And yes, I think it's even more powerful, Lachlan, to say it the way you said it, which is that this is an inverse square law. So this is related to a few concepts that ACER would regard as important that you are familiar with. And so one of them is, I'll put my nickel sphere here. Okay. So one of them is gravitation. So the formula for the force, for Newton's law of gravity, is a gravitational constant, m1, m2, the two masses involved, divided by r squared, which is the distance between the center of masses of the two masses. So notice it's an inverse square, which means if you double the distance, you quarter the force. You triple the distance, you have 1/9 of the force. Those types of relationships ACER plays with in many different ways. Also, it's not just gravitation. It's not just electromagnetic radiation, which we are looking at, and your understanding of the concept that there exists an inverse square law is important to solve the problem, essential to solve the problem. But it's also for Coulomb's law. Coulomb's law is for electrostatics. Opposites attract, like charges repel. And when you're calculating the force in electrostatics, it is, again, very similar to Newton's law of gravity, which is the force is equal to K, which is the Coulomb's constant, Q1, Q2, the 2 point charges involved, divided by r squared, the distance between the point charges. And so you see that this idea of an inverse square law comes up again. And you might wonder why. And it's because of this. It's because of a sphere, because the surface area of a sphere is 4 pi r squared, which you probably don't need to memorize if you if you are familiar with inverse square laws, which you essentially should be. Um, Okay, so we have this, and then finally we have two signals for question 89. So 87 we said was B, 88 is indeed C, and 89. Do you have an answer for that? So we have two signals of the same frequency transmitted to Earth. Um, and Q has 100 times more energy than P. Suppose the minimum intensity at which the signals can be detected. Q can be detected up to, so 89. Okay, so let's let's see. First of all, what is a watt? Could you give me other units for watts? Other units for watts. Well done, Lachlan. But yes, Daniel, we'll go with that. Um, so watt is a joule per second. Now, and we have this over meter squared. Now, the reason I'm bringing that up is because the question is saying intensity is remaining constant. Okay, so there's no change in the intensity when we're comparing the two different situations. And it also says that the frequency is the same. It says the same frequency. Now, what that does is it says that this is also constant. So, so we have the intensity is constant, and we have the frequency constant. Now, in this same exam, GAMSAT Practice Test 3 from ACER, question 5 is a question that brings up frequency. And of course, frequency is the inverse of time. So commonly, people remember it as frequency is 1 over the period. It's actually the time period, T. And so 1 over S is going to be constant. That's the frequency. And so all we're going to do is we're looking at manipulating the energy. So work and energy are in the SI units, joules. The question is, why is intensity constant? Because in the question, it says there is a minimum intensity at which these two signals can be detected. So we're going to be looking at the minimum intensity for these signals. And so we're comparing these two at the same intensity and with the same frequency. And so if you multiply, remember, we need to keep all this constant. If we multiply the numerator by 100, then the denominator must be 10 times m, so that when it's squared, it's 100 and the hundreds cancel. So will intensity be on the next exam? It's possible, but it is very likely that there's going to be some law that has either an inverse square, direct square, relationship, or logarithmic, and they're going to ask you to change one thing and see how it affects another. And so there are simple ways to set it up so that you can see, if I alter this, if I want the other thing to make sure that the overall equation is the same, how can I do that? Now, if you do happen to have the Master Series book, this intensity is discussed in section 8.3, and the gravitational equation in 2.4, and Coulomb's law 9.1.2. I'd like to give you a little caution, though, about, indeed, 89 is going to be B. So it's going to be 10 times as far. I do have a little, so it's 10 times the distance, which means it's going to be, for example, 10 times R. Okay, so I do have a caution for you, and it's about the gravitational equation, because that's a very important inverse square law. But there's something special about it as compared to Coulomb's law. And that is, you heard me say when I described the gravitational equation that it is the distance between the center of masses of the two masses. That concept alone is something that ACER enjoys. Well, I hope you will enjoy it too. So when you look at the equation, so we have the gravitational constant m1, m2 over r squared. So let's say the simple things out loud. If you double one of the masses, you double the force. If you triple one of the masses, you triple the force. You double both masses, you have 2 times 2, you have 4 times the force. As I said before, if you have 2r, meaning you double the distance between the center of masses of the two masses, you have a quarter of the force, because the 2 is going to be squared, just like down here. And if you triple the distance, you triple r, 3r, you square it, so you're going to have 1/9 of the original force. You can just look at it and make those manipulations. However, so let's say you have two, there we have you have this satellite. You have this satellite in orbit around a planet. Yes, that is a cut shuttlecock or badminton bird. And you have it in orbit around the planet. And the planet implodes. And now the planet has half of its original radius. How does that affect the gravitational force? The planet implodes, which is the exact opposite of exploding. Okay, so its radius has been reduced by half. How is the gravitational force affected? You see, so this is just one of the games that can be played, is that the gravitational force is unaffected. You see, this is, I'm sure that the person who designed this equation did not mean to trick students throughout history, but that R, it doesn't stand for radius. It stands for exactly what I mentioned before. It stands for the distance between the center of masses of the two masses. If the distance, the center of masses of the two masses is unchanged, the radius of this sphere is irrelevant because we're only measuring from here to here. Did the mass change? No. Did either of the masses change? No. Gravitational constant is a constant. It doesn't change. So your focus is solely on the distance between the center of mass and this, irrespective of the shape of this mass. Now, you might wonder, why did they ever do this to this equation? And it's because another issue that could come up on the exam is if you're standing on the earth. Now that's different. If you happen to be right on the earth as you are right now on the earth, then if you're going to measure the gravitational force between you and the planet Earth, well, then R is approximated by the radius of the Earth because you're so tiny compared to the Earth and you're really on the Earth's surface that your center of mass, what is it going to be? Less than a meter. Okay. So your center of mass is just above the Earth's surface. So to estimate the distance between the center of the Earth and your center of mass is reasonably estimated by just saying the radius of the Earth. But once you have anything that's interplanetary or outside the Earth's surface, well, then yes, then this distance becomes very important, and it's not the radius. Does that sound clear enough? And without trying to warp your mind, uh, this is, even though this equation has been so powerful over 100 years, that Newton, came up with a couple 100 years, and it's been so powerful and has allowed landings on the moon, landings on a particular crater on Mars, just outstanding things. It's probably all false. It's probably that there is no force of attraction between masses, and it's probably that the mass itself warps time space and creates a wave, and that the mass is following within the wave and has no choice as it's trying to get out. So it's probably something like that. But if that comes up on the exam, ACER will explain it and give you an equation, and you'll just be manipulating it. So basically, you'll be provided something and you'll be following the rules. Okay, so question, but if the planet has half of the original radius, doesn't that mean that the distance between the two masses decreases? But Julie, you're not saying it in exactly the correct way. So if this implodes and its radius is down to half of its original radius, my question to you is not is this: has the center of mass changed? Because if this implodes exactly where it is, where you see it right now, then the center is still the center in the middle of the entire sphere. And so its center of mass didn't change. Its center of mass didn't change, even though the distance between the satellite and the surface did change. Absolutely, between the satellite and the surface. But the equation is not about the distance between one mass and the surface of another mass. It's the middle of the mass. And if this implodes around its center, which is what implosions on an astronomical level usually would be, if this implodes, then the distance between this and the surface would have changed remarkably, but the distance between the satellite and the center of it would not have changed. I hope that's clear. The next question, I thought it was that the gravitational constant would change because there's less of the planet. So that gravitational constant is seriously constant. So it doesn't matter things exploding, the Big Bang, how the universe expanding, contraction, all of that, stars, all of that. The gravitational constant is constant for classical physics. Admittedly, Einstein has has brought up some issues in black holes where it probably doesn't, work. And there still needs to be some, data in some other, aspects. But for classical physics, which means for this exam, you accept G as a constant, you accept K for the Coulomb's constant as constant, and it cannot change based on what the mass is, unless ACER adds a note that section in black holes, something else that is possible. Okay, other questions? Uh, Same goes for yes. If point charge, okay. See, you're asking me about Coulomb's law and point charges, but uh, for Coulomb's law and point charges, the idea of a point charge is that it doesn't have size. It, you know, it it's so tiny that we do not discuss whether or not the point charge has a radius or a diameter or something like that. A point charge is saying that the charge acts as if it is at that very, very precise point and no other. That's different from, for example, having a metallic surface like this and charging the metallic surface. Coulomb's law is not intended to solve for that situation. It's intended to solve for situations where you draw it like this, you draw it like that, and then you're talking about what is the force between these charges. But it's not that this is a sphere and this is a sphere. It is literally a point charge. Okay, so right, okay. So with the example you mentioned, when a person was standing on the planet and it imploded and the radius halved, then the force would increase. So, uh, so yes, yes, exactly. So if you have a situation that somebody is standing on the planet and the radius is halved, then the force of gravity, as you correctly deduced, would be 4 times original. Okay, so that means we have 1/2 r, and that's going to be squared. So that means we're going to have uh, this is going to be changed to r squared over 4. So I square the r and I square the 2. So I have r squared over 4. And you can do this by cross multiplication, or you can remember the little song, the denominator in the denominator is the same as a numerator. So the denominator that's in the denominator is the same as the numerator. So we have the force is 4 times G m1 m2 over r squared. So if you're on a planet and it implodes, try to get off the planet because gravity at 4 times what it was before uh, will not be very comfortable. Okay, so any other questions? Oh, and by the way, that is the image on the front page of the Master Series GAMSAT book. That is what mass does to space-time. It creates these curvatures in real life. Well, yeah, in real life. That's our current understanding. And so if there's a satellite, it's going to keep, and you give it velocity, it's going to keep moving along the path because of the curvature in space-time caused by the mass. But in classical physics, the mass is actually attracted to the other mass, according to Newton's law of gravity. Okay, so that's it for today. Good luck with your studies. And if you're attending one of the tutorials, I'll see you in a few minutes. And if not, yes, there's still time. Practice and practice some more to get to where you want. And by the way, I think you guys know already, there's a free full-length exam on our website, gamsat-prep.com. It's a free full-length exam, and it has a lot of questions and detailed work solutions that are also free that will help you along. So good luck with your studies, and see you in the next one. Bye for now.